Well, I'm going to try to keep this video short because two other videos that I've made kind of give you a lot of the background you need for it. First is how to describe a simple oscillator, a mass on a spring, using a differential equation. Turns out that differential equation is sort of the key to being able to describe the behavior of such a thing. Like, why is it periodic or sinusoidal, as we sometimes call it? How can we describe what the period of that oscillation is? And then the next video was a simple pendulum. If you took a small mass, like a ball, and put it on the end of a fairly long string and watch it bob back and forth, that's what we call a simple pendulum. Turns out its differential equation to describe that is in almost an identical form as the simple oscillator with the mass on a spring, and so the descriptions of those are almost identical as well. And so this one that we're going to describe here is called a physical pendulum. And the only thing that really distinguishes a physical pendulum from a simple pendulum is that the mass is not all concentrated at a little point. So I've got an example here of, just take a ruler with a hole in it, and it will swing back and forth, but the mass is pretty evenly distributed along the whole length. It's not all concentrated down at the far end. So that's why it's called a physical pendulum. You could swing almost anything that way. Like you swinging on a swing set on a playground, you would be considered a physical pendulum if the chain on the swing isn't too long. So we sometimes draw just a generic shape here, something like that. And here's a rotation axis. So you got to picture this thing swinging back and forth. Usually, maybe the rotation axis kind of looks like this. And then somewhere is the center of mass of this thing. It's kind of an oddball shaped thing, so who knows where that is. But we'll just mark that here with a little x. This is the center of mass. And so, as we did with the simple pendulum, we describe the angle that the pendulum makes from vertical. And so that would be like, let's say this length here through the center of mass. And this is a lot on this little figure here. I'd encourage you to go to your textbook to see a more detailed version of this, because they have highly paid graphic designers that can make this look better than me. But this angle here is theta. So it's important that when we're swinging these things back and forth, we keep the angle small. And if you saw my previous video on the simple pendulum, you know that's because we're going to use something called the small angle approximation. So we describe this thing by using Newton's second law in rotation form, because it's not something moving linearly, it's something moving angularly. And that starts with torque equals I alpha. Okay? So what is the torque? Well, there's a torquing force on this that the component of its own weight that tends to pull it back towards that vertical. And so if we just draw the center of mass of this thing, then the weight would be straight down. That's mg. But the component depends on what angle this thing is at. So if we have it kind of at an angle like this, then the component, and that's what we refer to as the restoring force, the component there is called the restoring force, would be mg sine of theta, very similar to a simple pendulum. So this is our torquing force. And so the torque itself would be described first with a negative sign, because a restoring force is always opposite whichever way you rotated it. This restoring force, as I've drawn it here, is counterclockwise because my swing is up in the clockwise from vertical. So that's why we're using a negative. And a torque is the force, mg sine theta, times how far that force is located from the rotation axis, which is this length here from the axis down to where the center of mass is. So we've got to give that some kind of parameter, and we're going to use another little L for that. So the torque then would be that force times that L. Now this is any old generic shape, and so we're not going to use the moment of inertia expression for a simple pendulum. We're just going to call it I, and that'll be one of the parameters that you'd have to be given, or maybe if you know what the shape is, you can figure out what I would be. And then as we did before for the simple pendulum, we're going to describe the angular acceleration as the second derivative of angular position. And we write the second derivative this way, d2 theta dt2. And now we're going to employ the small angle approximation. Again, you can refer to a textbook or my previous video for that. But what that allows us to do is we get rid of the sine function. It's really great. So we now have negative mg theta L equals I, second derivative of position with respect to time. And I'm just going to write this in a slightly algebrated version, which is putting the second derivative all by itself on one side. Oops, forgot my 2 here. There's the second derivative. That's, again, that's a clever form of acceleration, angular acceleration. And then we have negative, and I'm going to put everything over here, mgl, those are all parameters, over I, another parameter, and then my variable is theta. That's kind of why theta gets set off by itself here. Kind of like we set x off by itself when we did this for the simple oscillator with the mass and a spring. So here again is this very important form. In your calculus class someday you'll learn the name for this particular type of differential equation. We need not get into that here, but all we see is that the second derivative is directly proportional to the negative of the variable itself. And so that is the hallmark of some kind of periodic harmonic motion, we call it. And so we can describe this with a period expression. In this case, the period of a physical pendulum. They always have this feature of having 2 pi in the front, and then a square root, and then you take this expression here, the coefficient of your constant, or your variable theta, you flip it over, and that becomes the fraction under your square root. So there is the expression for the period of a physical pendulum. Okay? Again, derived in a similar way, starting with Newton's second law, which is the same way we derived the simple mass on a spring and a simple pendulum of a ball on the end of a long length of string. So again, something I want you to be able to derive, and most would expect you to be able to derive this because, again, nothing here beyond the scope of what you've seen before, going back to your study of rotation. We're just applying some special parameters that are pertinent for a physical pendulum. So I'm going to leave it there, let you practice that a little bit and apply it to different problems that you see, but I think you'll do great at this. Thanks for watching.